Hi everyone, I'm David MacIver. I'm here to tell you about the paper that Alastair, Donaldson and I have written about how test case reduction works in the Python library hypothesis. Just to give a bit of brief backstory, hypothesis is what's called a property-based testing library, which is a concept that comes from the Haskell library QuickCheck. And largely what property-based testing is it's a way to bring the techniques that are fairly familiar to anyone who works in software testing research of test case generation and reduction and integrate them into a developer's standard testing workflow. It's, broadly speaking, tends to be quite simple from a quality of testing research point of view, and is largely focused on making these techniques as accessible as possible, which means it often has some interesting and slightly different problems than we would normally work on in the broader testing research. This is, as I say, about Hypothesis, which is a more recent property-based testing library that I originally wrote back in 2013 and has been getting a lot more traction in recent years. And here's a paper about it that we published in the Journal of Open Source Software last year, if you want to sort of know a bit more about it and why it's interesting more broadly. But to roughly show you what it looks like, this is a test in Hypothesis that we wrote and uncovered some bugs in Mercurial a while ago. It's fairly standard as property-based tests go. You have this given specification that says what sort of test cases you want to run your test against. You've got a test function which accepts an argument, and it checks that some property holds for any arbitrary value of that argument that matches the specification. And if it fails, you'll get an error like this, where you've got some exception. In this case, that our encoder produced a bad output, which couldn't then be decoded in turn. And you've got this falsifying example, which gives you a small, cute counterexample to the test that lets you see where exactly the problem is. And test case reduction, which we're talking about today, is basically the thing that means that you get an example that looks like this instead of an example that looks like this. Because Hypothesis, like most property-based testing libraries, uses random generation, often what will happen is you will have some large, complicated initial example that it found, because it was much easier to find a large counterexample, which it then wants to turn into this small example that you see here, so that users have an easier time debugging. The idea of test case reduction it's also been around for a long time. Sort of the classic paper on this is Zeller and Hildebrandt's Simply Isolating Failure-Inducing Input, where they introduced one of the standard techniques called delta debugging. And there's been a bit more research on sort of more specialized test case reducers since then. And test case reduction has been used in property-based testing from very early on. It's mentioned in the original QuickCheck paper as an aside, and has had some interesting research on it, but has mostly just been used as a fairly pragmatic tool that everyone just treats this as, of course, the thing you do in property-based testing. The problem that we're going to be looking at today is something called the test case validity problem, which was coined by Regier and al. In their work on the test case reducer CReduce, where it's a particularly bad problem, because the problem they had to deal with is that sometimes C programs have undefined behavior, and it doesn't really matter if you have a wrong code bug in a C program that has undefined behavior, because it's not really a bug, it's allowed to do anything. And so the test case validity problem is this issue where there is some fairly natural test you can write, in the compiler case, differential testing against multiple compilers and flags. But this test has some domain on which it's supposed to run. And outside of that domain, it might pass or fail, but that doesn't mean anything because it's not actually a valid test case to which it's supposed to have applied. And the test case validity problem is a pain for this sort of generate and reduce approach, because often it's much easier to construct a valid test case than it is to check if an arbitrary test case is valid. In their case, they have CSmith, which we'll talk about a little bit more later, which can easily construct valid C programs, but then CReduce has to use some sort of complicated validity checker to make sure that the programs stay valid while it's trying to produce a smaller counterexample. And here's an easy example of this coming up in Hypothesis, which is that suppose we had modified our specification to say that we only are interested in binary strings of size greater than or equal to 1. Then this initial assertion should always pass, because we've asked for strings of size greater than or equal to 1. And when we run the test, instead what happens is it fails, because we were given an empty string. And what will have happened here is that we'll have got that same initial large counter example we had beforehand, and then the test case reducer will have run, and it will have said, oh, it's a string, let's try replacing it with an empty string, see if that works. And because it only knew how to generate things with that min-size 1 and didn't know how to check whether something was a valid test case under that spec, the result is that you've got a real bug, which is then reduced to a bug that just happens because you're not satisfying the preconditions of the test. And although this is trivial, we could have the generators just add a predicate along with it. The thing is, the generators are supposed to be composable, and so you might be able to map an arbitrary function against the generator, and then you'd have to reverse this function in order to be able to check the precondition, which obviously you can't do in general. The traditional approach is that you add an explicit predicate precondition to your tests, which mirror all the things that you've already done during generation. And you can do this, it's not like the end of the world, but it's both kind of annoying to do and it's also easy to get wrong. And as your generators get more and more complicated, it gets more and more annoying to do, and it's easier for them to get out of sync. So ideally what we would like is this situation, where the precondition is automatically satisfied because you'd already asked for it in the generator, and you as the user don't need to do anything at all. And this happily is the situation we find ourselves in with hypothesis, because of the approach that I'm now going to tell you about. The key idea is that rather than trying to actually do test case reduction to the generated values, we wanted to do it by manipulating the generator itself. We wanted to persuade the generator to generate a smaller test case as if it had just gotten implausibly lucky and just happened to produce a really small test case by chance. And we do this by noting that random generation is basically built on top of an underlying predicate of drawing bits uniformly at random. You've got a getRandBits method on your standard pseudorandom number generator, and that gets used to make all the non-deterministic choices. But you could equally just treat this as reading the next n bits from some fixed sequence of bits. You can obtain this sequence of bits uniformly randomly initially, and then record it as you do, and now you've turned an arbitrary uniform random generator into this format of reading from a sequence of bits. We call these sequences of bits choice sequences, in that they represent the non-deterministic choices that we made during generation. And so any randomized test is basically just parsing some choice sequence. And with the parsing operation being the non-deterministic choices we make. And so as a result, we can apply any sort of conventional test case reduction to the choice sequence itself. And by doing so, we will reduce the size of the generated test case, because every part of the test case that we've produced involves some non-deterministic choices that we made in producing it. And so this won't necessarily be a perfect proxy for the size of the generated test case, but we found that in practice it's usually pretty good. And we call this approach internal test case reduction in order to contrast it with external test case reduction, where you apply it to the generated values. This is instead internal to the generation process. And to see how this works, let's imagine this is our binary generator. This doesn't implement min size just for convenience. We are repeatedly drawing some bits to decide whether to continue. Here we have a 75% chance of continuing, just to make sure that our binary strings are reasonably large. That is, we draw 4 values and only one of them results in stopping, which is why we have 75%. And then each step, if we're continuing, we draw 8 bits, which we add to the result. And you can see the parsing operation looking like this. Initially, we have this entire choice sequence waiting for us. We draw 2 bits, the first 2, which results in us deciding to continue on. We draw 8 bits, which gives us the first byte in our output. And then we carry on doing this: 2 bits, continue on, 8 bits, draw a byte, 2 bits, continue on, 8 bits, draw a byte, 2 bits. And then these final 2 bits are 0, 0. So this draw bits call returns 0, and we stop. The loop is done. We've returned our result. And in order to make this, in order to then reduce the generation value, for example, suppose we can do this by manipulating this choice sequence so that we can skip over parts of the loop iteration. For example, suppose we wanted to delete the first element. We could just cut out the first 10 bytes of the choice sequence, and now we skip over the first two draws and start on the third. And so we have, again, this 2 bits, add a byte, 2 bits, add a byte, 2 bits, we're done. So because the loop iterations correspond to continuous regions of the choice sequence, relatively simple deletions can end up deleting the final result as well. This was obviously a really simple generator. Does this work on more interesting generators? Yes. We've been using this in production since 2016, and generally it's produced very good results. Obviously, I need to show you that to you. You shouldn't just take my word for it, but we do have the experimental data, which I'll go over briefly now, and you can see more of in the paper. But the main sort of really interesting thing to consider here is also just like how dependent is this on hypothesis generators. Hypothesis has some quite well-tuned generators that are obviously designed with the fact that they're going to be used for internal test case reduction, and it's not necessarily clear how much that matters. And some of our experimental data tries to show that the answer is that it matters, but not as much as you might think. So we ran 4 experiments, or 4 classes of experiments. The first was just a bunch of synthetic benchmarks that we used to compare hypothesis against quick check. These were ones previously developed for another test case reduction in paper about a tool called SmartCheck. We ran some tests on SymPy, which is a symbolic algebra library that has lots of bugs, so it's really convenient and for testing on. Reusing a previous harness from another paper, that uses a language called TSTL, which is designed for testing Python APIs. Custom generator of Python programs. You don't need to know that much about that right now. Read more in the paper if you want to know more. And the most interesting one is that we modified CSmith, which is a fairly complicated generator of C programs that has had quite a good track record finding bugs in C compilers. And we generated a bunch of real bugs in old versions of C compilers and drove CSmith with hypothesis to show how well the internal test case reduction works on that. And sort of at a high level, the results are basically this, which is that if you look in terms of cost of actually getting to the final reduced results, everything's basically fine. Hypothesis is sometimes the fastest, it's sometimes the slowest, except in some pathological cases for quick check where it just performs much worse than everything else. Nothing is really more than an order of magnitude worse than anything else, and there's not much to see there. Hypothesis is it's usually a bit better than quick check, except for on 1 or 2 of the benchmarks, but there's not much in it. And on the external reduction, it's slightly better than delta debugging on some things and slightly worse on others. And so, from one point of view, this is a relatively uninspiring set of results, but actually this is what we consider success, because the real goal here is to solve the test case validity problem and also be about as good as the alternatives that don't solve the test case validity problem. We were not expecting to sort of blow the other alternatives out of the water, and so having this sort of everything's basically fine result, plus we've got this extra property, is really what we want here. One interesting thing is that we do hit some intrinsic limitations with CSmith, where hypothesis actually does a very good job of reducing CSmith things. We were quite surprised, but there, this property of always reducing to things you could have generated isn't actually entirely. It's something that makes blessing, and you can sort of see this because of this example, which is the smallest thing that CSmith can possibly produce. And so you see you've got all of this extra boilerplate here that wouldn't necessarily be necessary in a fully reduced example, but because CSmith will always generate it, so will hypothesis reduced test cases. And here is an example of a hypothesis reduced bug. This is a crasher bug in GCC, I think, and it isn't much larger than the minimal test case, and most of the extra size on something you would reduce with delta debugging or the like comes from that extra overhead. There's a little bit more on top of that, but that seems to be most of the big differences. Just to conclude, internal test case reduction is the approach we're using in hypothesis. You can use this to integrate test case reduction into any random test case generation you like. You do this by interpreting the random test case generation as parsing and using conventional test case reduction to the parser. And this solves a large class of test case validity problems that we run into in proper data testing by maintaining this guarantee that reduced test cases could in principle have been generated. And our experiments show that this is an idea that has a lot of promise outside of hypothesis, and we would sort of encourage you to read the paper, find out a bit more how it works, and see if you can apply this to your own test case generators, because we think it's a useful and underused technique. Thank you very much.